if we assume, as they say, that it has just vanished, like it melted instantaneously, if it really melted instantaneously, yes, we can have the crashing case. We can have, so this is what we will assume. I'm going to assume the most optimistic cases in favor of the theory of the structural failure, or the official theory. So we will assume that one floor vanishes instantaneously, is this floor, and we will start calculating what would happen with simple physics equations. The spacing between each floor is 3.8 meters. I will calculate the speed of this block when it hits the bottom, when it comes all the way to here. So this block, first we assume that this floor vanished instantly, and now this block is gonna accelerate down and smash into this here, what's below it. So now I'll calculate the velocity that it will be at when it hits the bottom. The equations are very simple, these ones. The straight line equations for constant acceleration. This is a high school physics book. So that's v is final velocity, u is initial velocity, a is the acceleration, and d is the distance. Now, first thing, we have to take a convention. We will take up as negative and down as positive. This is our convention, and we'll use that and we'll be consistent throughout the calculations. So now v squared equals u squared plus 2ad. We have the block at the beginning, initial velocity is 0. We substitute 0, and then v squared equals 2 by the acceleration. The acceleration will be the acceleration due to gravity, which is 9.8, and it will be downward, so it's positive 9.8, multiplied by the distance, which is the spacing between the floors, 3.8 meters. V squared is 74.48, and therefore V is 8.63 meters per second. This is the velocity at which the top block will crash into the bottom. This so far hasn't been encountering any resistance except for the air resistance, and we ignored the air resistance. But as soon as it hits the building, it will encounter resistance from the structural skeleton that's existing here, which is untouched and strong. So therefore this block will experience a resistance force from this existing structure below it. Now, how big is this resisting force is what we will try to determine. So I'm going to draw the resisting force with red. This resisting force will be at least as big as the weight of this block, at least. And this is obviously another extremely optimistic assumption in favor of the official theory. So now we will calculate how big this force will be. I'll take a free body diagram on this block. The only force acting downwards on this block is its weight, which is mg. And the resistance force acting on it is at least the mg, because it has always been supporting this. This structure has always been supporting this block in the past 30 years. So it will offer an average force of at least the same amount or the same size as the weight. plus, so the resistance force will be mg plus, and the building was evacuated at the time of the incident, so it's designed to carry the weight of the people as well. So that's 123 people for each floor, 15 floors, and about 84 kilograms for each person by 9.8. So this is the humans, this is the weight, plus the humans, plus the safety factors. Because whenever they design a building, they don't design it just on the edge. Because let's say some people were watching a soccer or football match, and someone scored a goal and all the people jumped at once. If they've designed it right on the edge, it will collapse, and therefore the minimum resisting force will be the mass plus the humans plus the safety factors. Now again, I'll be optimistic and I'll ignore the safety factors. Let's assume that they did not have any safety factors, and we'll just take the humans weight. So we have a block here, we have mg newtons downwards and mg plus the humans weight newtons upwards. So will we have an acceleration downwards or a deceleration? That's the big question. Will this block accelerate downwards or will it slow down? The answer is obviously it should slow down. So the speed of the block should never exceed 8.63 meters per second. We obtained that by assuming that the floor here just vanished and there was no air resistance, and the block just accelerated full blast until it reached the bottom structure. That would give us 8.63 meters per second. Then it started collapsing the building below it and crushing it as it's going. So in this case, it will be faced with resistance from the structure of the building, and this amount of force will be at least the same or bigger than the weight of the block, because throughout its history it has been holding this block. So even if it's gained some speed to be able to crush something from the inertia, it still would be slowing down, not speeding up. So I'll do it mathematically and you'll see sum of the forces in the vertical direction equals ma. That's Newton's second law of motion. It will be faced with resistance from the structure of the building, and this amount of force will be at least the same or bigger than the weight of the block, because throughout its history it has been holding this block. So even if it's gained some speed to be able to crush something from the inertia, it still would be slowing down, not speeding up. So I'll do it mathematically and you'll see sum of the forces in the vertical direction equals ma. That's Newton's second law of motion. Now I'll write down the actual masses here. The mass of this block of 15 floors is 68,000 tons, which is 68 and to get the weight I multiply by 9.8. So the weight of this block is 668,181,816 newtons. Now this this one here, the resistance force will equal 669 700,620 newtons. Now this is going to be negative because it will be acting upwards. It's the resistance from this structure. Now what we have now, we have two forces in the opposite directions. This is one and this is one. The sum of the forces in the vertical direction is equal to ma. So now I want to work out the acceleration. So sum of the forces will be this plus that, plus 668,181,816 equals ma. So if you substitute the numbers, you'll find A will equal negative 0.0223 meters per second squared. So therefore we have a deceleration here, we don't have an acceleration as we expected, because the net force is upwards, not downwards. So this block that's falling is going to decelerate, it's going to slow down, it's not going to speed up. So now we will see how long for this block to reach the ground. How long will it take for this block to crush all the way to the floor? Now I will work out how long it will take for the block to reach the ground. Another simple equation. I write down my information. When the block is hitting this structure, the speed of it is 8.63 downward, so it's positive. So the initial velocity is 8.63 meters per second, and the acceleration, I put it here, is negative, it will be upwards. So my distance, and the distance will be 361 meters. It's the distance from here to here, 361 meters. So this is the formula again from the straight line motion formulas that I showed you before. This is d equals ut plus half at squared. Constant acceleration formula, so 361 equals u, which is 8.63. 361 is down, so it's positive. 863 is down, so it's positive, by t plus half. The acceleration is up, so it's negative. Negative this value, 0.02 t squared. So as you see here, I've got a quadratic. If I solve this quadratic, my t will come as 44 seconds. So the building, if it was to crush what's below it, it should have taken at least 44 seconds. This is obviously not the right way to calculate, but this is at least. This gives you is a very simple way to give you at least how long it will take for the building to reach the floor. Now in reality there is a lot of energy is used to deform the structure, and a lot of energy, as you saw, this is assuming that the whole block is falling on. When you saw in real life, it was all falling away, so this structure had no reason to collapse. Also, this structure, as you're going down, it becomes much more stronger and more solid, and that's the design of it. So it would not make sense for it to crush it at all, but this is just for the argument's sake and to see if it's possible. And as we saw, it fell in 10 seconds, and if it was to crush all of this and there would be no resistance from the structure except its own what it was already supporting, then we still find out that it will take 44 seconds for the block to reach the floor. Alternatively, if we say that the building was not designed to hold humans, and this block here, this structure, would provide resistance as big as the weight of this block, which it has always been holding for the past years. So if we assume that, so we say this structure will provide a resistance force equal to the weight of this block. Still, the sum of the forces after this block has hit this block, after it has accelerated and hit this block, the sum of the forces now is equal, the same. So it's equal to 0, because you have the resistance force is equal to the weight force of this block, and they're in the opposite direction, so the sum of the forces, or the force net, equals 0. So when the force net equals 0, there is no acceleration. So whatever the speed that was, which is 8.63, it should stay the same throughout the whole journey. And if we do that calculation, if we do, v velocity equals distance over time, this is very simple equation. If we say the speed or the velocity was 8.63 and the distance was 361, so how much time should it take for this block to reach the floor? It will be 42 seconds. So this is, if we assume there was no humans, it's not designed to take the weight of the humans, it should take 42 seconds to crush it. And if we assume that it was designed to take the weight of the humans, it should take 44 seconds to crush it. But none of them shows that it can take only 10 seconds to crush the whole thing. Thank you.
We heard this rumbling sound like a terrible thunderstorm, and we were just running and running and running. Then I heard a big push.
The tower that had taken 10 years to build collapsed in 10 seconds.